Hello everyone, welcome to my YouTube channel. So today I am going to discuss about path connectedness of R2 minus Q2. This is a very important question because in TIFR previous year question paper, in NBHM as well as in ISI entrance exam also, this question was asked, and also in many interviews this question was asked. Okay, so this is a very important problem, and in 2024 ISI subjective exam paper, this same question was came. Okay, so this same question was there, so that's why it is important. Okay, so let's start. Okay, so how do I show that? So the question usually comes in this way, right? That R2 minus Q2 is path connected or not, or in particular R2 minus Q2 is connected or not sometimes. So since R2 minus Q2 is path connected, so it will imply R2 minus Q2 is connected. Okay, so how do I show that R2 minus Q2 is path connected? And the proof is actually holds for R2 minus any countable set. So general statement is that general statement for any countable set A, R2 minus A is path connected. So we will solve this problem completely by geometric intuition. So how do we solve it? So if I want to show that any set is path connected, then we need to show that if I choose any 2 points, then there is a continuous path joining that 2 points, right? So choose 2 points P and Q belongs to R2 minus A. Okay, okay. Now, how many lines can you draw in R2 passing through a fixed point P? How many lines can you draw? So if it is R2, say this is the point, then how many lines can you draw from that passes through this point? You can draw uncountable many points, right? Sorry, you can draw uncountable many lines, right? Passing through this point P. How? So in particular, if you, without loss of generality, if you assume that P is origin, then in R2, if you consider it as R2, say this is x-axis, this is your y-axis, and this is the point P, then any line passing through this point origin is basically given by y equal to mx. Now you can take m to be any real number. That means you will get uncountable many different lines passing through origin, and that same thing you can do for any point P. In particular, you can just translate that these lines, and you will get that the uncountable many lines passing through point P, right? So first observation, we get uncountable many lines passing through P, and similarly we get uncountable many lines passing through Q, right? Okay. Now if I fix any 2 point, then in R2, then there exists a unique line, straight line passing through these 2 points, because if we have 2 points and if we have 2 coordinates, then we can find the equation of the straight line. right? So there is exactly one straight line passing through this. Okay, so in particular, for any point x in A, we can draw a line passing through P and X. So for every x in A, we can get a line passing through P and X, right? So that means, and if I fix any x, that means there is exactly one straight line that passes through P and X, right? So that's why this will imply we have countable many lines, because A is countable, such that for each A belongs to A, LA denotes the line, say LA comma P, passing through A and P, right? Now if script LP, collection of all lines passing through P, then this collection is uncountable, and LA comma P is a sub collection of this script LP. Okay, and this is non-empty. Clearly this collection is non-empty because script LP is uncountable, and capital LA comma P or capital LP, which is, it's not A comma P, it's better to write LP, which is union of LA comma P. Okay, right? So this collection is non-empty. Similarly, we can do the same for Q, and we have LQ minus, this is non-empty, right? Okay, so if you choose any line, then all the points on L are not contained in A, because we have already removed that lines. Because if any point on L is or in A, that means L is the line passing through P and that particular point. But we have already removed that collection from this big collection, right? So that means if xy be any point on L, that will imply that xy belongs to R2 minus A, right? Okay, okay. So now how do I approach it? Okay, so then say here it is P, here it is Q, here it is X, which is belongs to R2 minus A. Then we have a straight line joining P and X, and this straight line is inside script LP minus capital LP, because this X is in R2 minus A, right? Okay, And similarly we can do the same thing for Q. We can do same thing for Q, right? Then we can get a path joining P and Q, right? So this is our idea. Now how do I do that explicitly? So explicit proof, this is the idea, right? So this is the idea that we will have a continuous path joining P and Q. So how do I prove it? So choose any line L containing script LP minus capital LP, and choose any line T belongs to capital LQ minus small lq, right? So we can choose T such that T is not parallel to L. Okay, because why we can choose that? So see, this is P and say this is L, here this is Q. So there exists exactly one line which is parallel to L, T, and T is parallel to L. So first we remove a countable collection LQ, then we remove this extra line which is parallel to L, and outside of that collection, that means we in particular we are choosing T belongs to LQ minus script LQ minus capital LQ union the line parallel to L. Okay, then L and T are not parallel, that will imply L and T must intersect, right? So say this is P, this is Q, here this was L, here this was T. That means this must intersect at some point A. And observe that since this L belongs to this script LQ minus capital LQ, that means all the points on this line is in R2 minus A. Similarly, all the points on this line is also R2 minus K, R2 minus A. That means we have a path joining P and Q. So we have a path joining P and Q in R2 minus A. Hence R2 minus A is path connected. In particular, R2 minus A is connected. Okay, and since Q2 is countable, so we can do the same thing for Q2. So you can just replace A to be Q2. Okay, that's all. So the same thing we can show for any countable set. The proof is same. I hope you all understand this. If you have any doubt, just comment below. Thank you.